Welcome back. In this section, we'll be looking at solving logarithmic and exponential equations. There's a bunch of different techniques, and depending on how our equation looks, we might have one or more techniques that might work for solving them. Now, one big thing that we'll need to keep in mind, and this was the same thing that was true when we were solving radical equations earlier, that there were some cases where we would have to check our solutions. If it was a radical equation and we squared both sides or raised both sides to an even power, it was possible that we might have extraneous solutions, so we had to check them. The same thing is true for logarithmic equations, because remember, for a logarithmic function, the inside can't be negative and can't be zero, and so that means there's a possibility that any value of x you find when you solve a logarithmic equation might turn out to be extraneous. So we will need to check our solutions for the logarithmic equations, and reminder that we'll need to check them in the original equation. Exponential equations, on the other hand, remember that an exponential function like a to the power of x, that the domain is all real numbers, and so it really doesn't matter. Any value of x we find as a solution should be something that's in the domain and should not be extraneous. You can check your solutions if you want, but it's only for the logarithmic equations, ones that had logs in them, where it's going to be mandatory for us to check our solutions. Also, again, we have to check them. We can't just guess, and we can't just assume which one must be the solution. Just like it was with radical equations, it's possible that we might find that all of the values are solutions, or none of them are solutions, or only some of them are solutions. So you will have to check all of your solutions for any logarithmic equation and confirm which ones are or are not solutions for the original equation. Okay, so our first technique is if we have a logarithmic equation where there's two logs, one log and another log, and that they both have the same base. So if we can get our equation to that point, where we have log base a of m equals log base a of n, we knew from the previous section that one of the properties of logs, since they're one-to-one functions, if the y values for our logs are equal, then the x values for our logs must be equal. So if you have two logs that are equal to each other, then the insides for those logs must be equal. Now, of course, that means that you might have to do some things first before you get it into this form of one log equal to another. If you notice here, we've got on the right side not just one log, we've got a difference of logs. And on the left side, we don't have a single log, we have a log times 2. But I know that one thing I can do, of course, with the 2 is to bring it up as a power, and that these two logs could be combined together using my log properties. So on the left side, natural log of x minus 1 times 2 becomes natural log of x minus 1 squared. And on the right side, natural log of 18 minus natural log of 2 becomes natural log of 18 divided by 2. And 18 divided by 2 is just 9. So using my log properties, I've rewritten it as natural log of x minus 1 squared equals natural log of 9. And since I have two logs that are equal to each other and with the same base, then I can conclude that x minus 1 squared is equal to 9. And of course, if x minus 1 squared is 9, then that means x minus 1 should be plus or minus the root of 9. And square root of 9 is 3. And so I've come up with two potential solutions here. One solution is x is equal to positive 3 plus 1, which is 4, or x is equal to negative 3 plus 1, which is negative 2. Now, I have that these are potential solutions. We still have to check to make sure that they actually solve the original equation. So this is one place where we need to be careful. When we're checking our solutions, we'll need to check both values, the 4 and the negative 2, and we won't be putting them into the second line that I have here. That would be incorrect. We don't want to know, do they satisfy this modified equation? We want to know, does it satisfy the original equation? So I need to make sure that I'm putting my 4 and also my negative 2 into the original equation to see does it make the left side and the right side equal to each other. So I'll start with checking the x equals 4. And if you were to put it into the left side, you would have 2 times natural log of 4 minus 1, which is 3. And 2 times natural log of 3, well, that would be natural log of 3 squared, and that's natural log of 9. The right side, that's natural log of 18 minus natural log of 2, which we know is the same thing as natural log of 18 divided by 2, which is 9. So left side and right side are equal to each other. So we've confirmed that, yes, 4 is a solution. But if we're checking negative 2, on the left side you would have 2 times natural log of negative 2 minus 1, which is negative 3. This is undefined. Remember that for logarithms, the inside has to be positive, and so since natural log of negative 3 is undefined, left side and right side can't be equal to each other. The left side is undefined, which means we're going to have to reject that value. And so that means that the solution that we have, the only solution for this equation, is the single value 4. So just like we had with radical equations, we might come up with multiple values for x. In this case, we had 2 values, 4 and negative 2, but it turned out that the negative 2 happened to be extraneous, and so the only solution happens to be 4. Now, you potentially might have it where you could rewrite it so that there's only a single logarithm. So instead of having one log equal to another, you might have one single log equal to a number. And if that's the case, you could then solve the problem by rewriting that equation as an exponential equation. This is sort of a common theme you'll see in a lot of these problems, that taking an exponential equation and rewriting it as a logarithmic equation, or vice versa, that's often a technique that we'll use to solve our equations. Now, of course, that also means that if you don't just have a single log, you might have some work to do before you have it as a single log. Here, I'm looking on the left side, and I have got one log plus another. I've got log base 3 of x plus 2 equals plus log base 3 of x minus 6, and all of that's equal to 2. I know that on the left side, if you have one log plus another log, and they both have the same base, that you could combine the two logs together by saying it would be, in this case, log base 3 of x plus 2 times x minus 6. And this could be rewritten as an exponential equation. We have log base 3 of something equals to 2, or 3 to the power of 2 is equal to x plus 2 times x minus 6. Remember that when we go from a logarithmic equation to an exponential equation, we're exchanging the inputs and the outputs. For the logarithmic equation, x plus 2x minus 6 was the input, so for the exponential equation, it becomes the output. And 2 was the output for the log, so 2 becomes the input for the exponential equation. And so now we basically have just a nice little quadratic for us to solve. So I have 2 possible values that I'm going to find. This factors out nicely as x minus 7, x plus 3, and I get 2 potential values for x. I get 7, and I get negative 3. And keep in mind, again, these are potential values because I'll need to check them in my original equation. That it's not enough to just trust that one of them or both of them might be solutions. We actually do need to check. So I'm going to start off by checking x being 7. The right side of the equation is always going to be just 2, so I really only need to make sure that the left side is equal to 2. And if I put in 7 for x, I'll have log base 3 of 7 plus 2, and log base 3 of 7 minus 6. So that's log base 3 of 9 plus log base 3 of 1. And that's easy enough to evaluate. Log base 3 of 9, 3 to what power gives you 9? The power is 2. Log base 3 of 1, 3 to what power gives you 1? It's 0. Also, you could use the idea that log base anything of 1 is always equal to 0. But either way, we get it's equal to 2, which is the right side of our equation. So that one works. Yay, we have at least one solution. Now we need to check x being negative 3. And if we put it into the left side of our equation, we run into a problem right away, because if we put in negative 3 for x, you'll have log base 3 of negative 3 plus 2, and log base 3 of negative 3 minus 6, and both of those happen to be undefined. And since they're undefined, that means we can't have the left side equal to the right side. So in other words, we must reject x being negative 3, so that the only solution happens to be positive 7. Now, you might be asking yourself, couldn't I have just assumed that since negative 3 is a negative number, that it would have to be rejected? And the answer is no, unfortunately. It's not just, is this number negative? It's the question of, if you put the number in the logarithm, does it make the inside of the logarithm negative? And it's possible, depending on how the equation is written, that you might have a value of x that's positive, but when you put it inside the logarithm, it makes the inside of the logarithm negative, and therefore you'd have to reject it. That's why I say you have to check all of your solutions. You can't just assume, because it's possible I might create an equation where you solve for x, and the values of x you find are negative, and they turn out to be solutions. You have to check them to make sure that they're solutions. You can't just assume whether or not they are. So there we go. We've looked at one case where you have a log equal to another log, and another case where you have a log equal to a single number. So we've ways to solve those problems. And now let's look at solving some exponential equations. Exponential equations, we've got a couple of techniques that we'll be looking at here. And one of the techniques is this, that if we've got for ourselves some sort of exponential expression equal to another, and that they have the same base. So if a to the power of m and a to the power of n are equal to each other, then the powers m and n must be equal to each other. And the reason why this works is the same reason why it worked for logarithms. If you're thinking about the exponential equation y equals a to the power of x, then these would represent the y values for that function. In other words, the y values are equal, so therefore the x values must be equal. That's the property of a one-to-one function. Since exponential functions are one-to-one, then we know if they have the same y value, then you must have the same x value. So let's use this. We have here 2 to the power of x squared minus 1 is equal to 8. And although it's not already written all with the same base, you could rewrite it with the same base if you recognize that 8 is the same thing as 2 cubed. So you really could say you have 2 to the power of x squared minus 1 equals 2 to the power of 3. So x squared minus 1 should be equal to 3. And so therefore x squared is 4. And so x should be plus or minus the root of 4. And there we go. I've got two solutions. My solutions are positive 2 and negative 2. I don't have to check my solutions here. I can if I want. If I have a few extra minutes, it doesn't hurt to do that. And you can confirm that if you put positive 2 or negative 2 in for x, it will make the left side and the right side equal to each other. But we don't have to do this, simply because for an exponential equation, its domain is all real numbers, so any value of x that I find should be something that's in the domain of this function. I don't have to worry about finding values of x that would make that function undefined. So here I have two solutions, positive 2 and negative 2. All right, so one more technique that we have is this is another one where we have another exponential equation, but this time we have only one exponential expression. So we have something to a power of m is equal to n. So we've got a bunch of techniques that we could use here, and one of them is that we could rewrite it as a logarithmic equation and then solve. Or another option is if you have something where the base isn't e or 10, you could still use natural log to help you solve your equation. So one thing that we could use is if we had the exponential equation a to the power of m is equal to n, and if I were to take natural log of both sides of the equation, then I would have on the left side natural log of a to a power. That power could be brought in front. And so I'd have m is times natural log of some constant, so natural log of a, that will just be a number, equal to natural log of n. So I would be able to now solve for m. I would be able to solve for what that power is. So let's do this first one. This one is 10 to the power of 3x plus 1, and it's equal to 2. And I'm going to rewrite this as a log. So since it's base 10, I'll be using log base 10 or common log and switching my inputs and my outputs. And I'm just going to now solve for x. So I'll bring the 1 to the other side. And then I'll divide by x, or sorry, divide by 3. And there we go. I have my one solution, which is log base 10 of 2 minus 1 all over 3. And there we go. I don't have to check my solutions here. Like I said, I can if I want, but this is an exponential equation. It's only logarithmic equations where I have to check my solutions. And so there we go. A couple of things you might have noticed that I did. I first started off writing it as log 2, and I didn't use any brackets. And then when I moved the 1 to the other side, I rewrote it as log 2 minus 1 with the 2 in brackets. And that was because, remember that for logs, we sometimes will need to use brackets if our meaning otherwise wouldn't be clear. If I just brought the 1 to the other side and didn't have brackets, it would be maybe not clear to somebody reading this whether it's log of 2 minus 1 or whether it's log of 2 minus 1. And so to make it clear what's actually going inside the log, that's where I put a little bit of brackets around it to help make it less ambiguous. The other spot just to be careful about here is when we're looking at our answer, log base 10 of 2 minus 1 over 3, a lot of times people will mistake this as meaning log of 2/3 minus 1/3, and these are desperately not the same thing. Remember that in this case, the only thing going inside this logarithm is the number 2. That 3 is what's dividing the entire logarithm. So the entire log base 2 is being divided by 3. It's not the 2 that's being divided by 3. That's the mistake that people might make here, is thinking that, oh, okay, if we're taking everybody and dividing it by 3, that's as simple as dividing the inside of my log by 3. And of course, that's not the same thing. So this one, I'm going to solve a couple of ways. I'm going to do it once, rewriting it as a log, in this case log base 4. So I have 4 to the power of x minus 7 is equal to 9. So you could rewrite it as a log base 4, switching the inputs and the outputs. And then there we go. We've come up with our solution, which is the single value 7 plus log base 4 of 9. And that's one way that you could solve the problem. And it makes perfect sense to do this since it's log base 4. That means that we won't know the approximate value, though, which means that although it's a nice little compact answer, if we needed to know what the decimal value of this was, so for example, if this were part of a word problem and that's why we were solving the equation, then this answer might not be super useful for us because we would then need to still figure out what is this as a decimal number. So you may find that it's nicer to sometimes, instead of using the log that associates with that base, in this case base 4, you might just use either natural log or log base 10, since those are functions that are on your calculator. So by that I mean, so here's my alternate solution. I could take natural log of both sides of the equation. And that means that that power, x minus 7, can come in front. I have x minus 7 times natural log of 4. Just expanding what I have on the right side. So x times natural log of 4 minus 7 times natural log of 4. And then I'll bring that 7 natural log of 4 to the other side. And then divide by natural log of 4. And I come up with another answer that looks different than the first one. That's a part of the reason why I wanted to do this example. Is one of the properties of logs is that change of base property, but that means as a result that there are going to be not just one or two ways that you might express your answer, but infinitely many ways that you might be able to express your answer if it involves logs. So although these two answers look wildly different than each other, and if you had one of the answers and the other one was the solution in the back of the book, you might think that you were wrong because they look so wildly different. But these are actually equivalent to each other. That if you were to rewrite these both as decimal values, you would find that they are exactly the same. That these are just different ways of expressing the same number. And in fact, you can sort of confirm that to yourself if you were to rewrite this as natural log of 9 over natural log of 4, then make common denominators. And then combine together, you can see how you would get to the same answer that we have over here. This answer, though, is maybe a little bit more useful to us because if we did want to know a decimal value for what is x, since it's already written in terms of natural logs, then this would be easy to do. I could just run and grab my calculator and find out approximately what x is. But either of these would be acceptable answers. If I'm looking for the exact value of what is x, both of these would be correct answers. All right, let's do one more. And so for this one, I don't have yet just a single exponential expression equal to something. So first thing that I would want to do is isolate my exponential expression. So I'm going to first bring the 2 to the other side, and then bring that 12 onto the right side, bring that 6 on up, making the right side 2 times 6, which is 12. And now, at this point, like I said, you could choose to rewrite this either as a log with base 3, or you could use natural log, whichever you prefer. I'm going to use natural log here, so if you want to confirm your answer with log base 3, you can, and see that they turn out to be equivalent, but I'll take natural log of both sides. That'll be how I'll solve it. And then now I have that the power, x squared minus 1, can come in front. And next, I'm going to divide both sides by natural log of 3. Bring the 1 to the other side. And then x should be plus or minus the square root of all of the right side. There we go. And so my solutions are positive root of 1 plus natural log of 12 over natural log of 3, and the negative of 1 plus natural log of 12 over natural log of 3's square root. There we go. And we have our two solutions. And again, we don't have to check our solutions because this was an exponential equation, and it's only for logarithmic equations that that's required. You might notice here that this natural log of 12 over natural log of 3, using your change of base formula, is the same thing as log base 3 of 12. So if you had taken your equation and rewritten it with log base 3, instead of what I have, you would have plus or minus root of 1 plus log base 3 of 12.